Doot, doot, doot. Okay, can people hear me through this thing, or do I have to turn the volume up? In the back, is this good? This is good? Okay. Okay, it is 1:15, so I'd like to start. First question is, are there any questions? Last class we were talking about hashing. Any questions or comments about hashing? How you build a plagiarism detector, anything like that? Any questions or comments about homework? You should have a homework. One is due next class, before next class. Am I correct? Do people believe that? How many people realize that? Who here knows about homework 1, right? 373? Any questions about homework 1? Yes?
I thought that it was due at 9.
What does it say?
Okay,
I like it to be turned in before class. Whatever the requirements are on the assignment is what it does, but I usually like it turned in before class so people come to class rather than work on their homework then. Okay? So any questions about that? Okay. Someone send me a mail if they want me to confirm when the real time due is, and we'll try to post it. But I like it in before class. If I have a say over it, that's what it'll be. Any questions? Okay. Any questions about the homework or anything? Okay. So we've finished what I would like to say is the unit on data structures, and we're getting into the unit on sorting, which I always find exciting. This, I believe, is the problem of the day. Am I right? Okay. The question is, you're given the job of making up, it says you're given 2n real numbers, and you want to pair them into teams, okay, such that the way you pair it up minimizes the largest sum of a team. Why would we want to do this? Before we actually do it, let's think, is there a reason why you might want to do this? Okay? Let's say you were going to be let's say you had a professor who cared about making all the project teams fairly balanced, right? Okay? Or if we don't have such a professor, let's imagine a world where you're making up tennis teams. You do not want the best and the best 2 tennis players to be on the same team. Why is that? Because they will crush every other team. Does everybody see that? If you want to try to come up with a fair way to make the teams, we need some kind of a criteria of fairness so that, try to make them as balanced as you can. And this one says we want to minimize the largest sum of a pair. Okay? So how do you do that? You're given, an even number of tennis players. This one has got skill 5. This one's got skill 8. This one's got skill 9. This one's got skill 23. This one's 24. And Roger Federer is a 51. Okay? How do you pair these up in general so as to make sure that the largest partition is as small as possible? Does anybody have an algorithm? Any questions about what the problem is? Does anybody have a proposed algorithm? Okay, I see twitching there. Yes. Sort them. Okay, that's a good start. Okay, you would put Roger Federer with Skeena, and you would put somebody else with a better player and stuff like that. That's what you're trying to say, right? Okay. Does this minimize the size of the maximum sum? What do we need if we want it to minimize the size of the maximum sum? We need a proof of correctness. Does everybody see that? Okay, does this seem like a basically good idea? Okay. Can anybody come up with an argument for why this is right, though? That's kind of what's kind of missing right now. I think a lot of people like this algorithm. Is it right or is it wrong? Okay. Can someone give me a proof? Yes. You want to give a proof by contradiction, and what does that mean?
Yeah, so we'll assume that because on the first pair, we're pairing up the maximum one with the minimum value. So we assume that we don't do that. We say, okay, we pair up the maximum one with a non-minimum value. Then it's guaranteed that for any other value other than the minimum one, that it'll always be larger than if you paired up with the minimum value.
Okay. What you're trying to say, again, this is a contradiction proof. What you're trying to say is, wait a second. Notice that if you don't pair up Roger Federer with Skeena, you got to pair him up with a real tennis player, right? And if you pair him up with this one, okay, the the result is that this sum is going to be bigger than that sum. Is that right? Everything he said is right. Is that a proof that this strategy is right? And the answer is no. Because what if the most unbalanced pair was not this one, Skeena and Federer? Let's say that in the middle we have people who are, let's leave that. I don't know what I had down there, but let's say 17 and 23. Let's say that doesn't matter. But notice that, suppose this was 50 over here. Do you see that this one was the bigger pair in the assignment rather than this one? What you're telling me is that it's true that if I don't pair the biggest one with the smallest one, the guy with the bigger is going to be in a bigger pair, right? That much you've shown me. But you haven't shown me that this necessarily, that changes the optimum. Notice that if these two guys are let me make a more dramatic example. Let's say that these guys were 48 and 49, right? Does everybody agree that these are now the biggest pair, right? And whatever you do with Roger Federer doesn't change what the biggest pair is, okay? So the best team is not necessarily the best player with the worst player, okay? What we want is an argument that over all possible assignments, we're going to find the assignment that minimizes the size of the largest pair, okay? Someone want to try again? Yes.
Maybe another way to think about it is that the most ideal sum, pair of sums, is always going to be the total sum divided by the number of numbers there times 2, because you're adding two numbers together. So the idea is that with the lowest number possible, you want to add the number that will get you closest to the average sum of the two pairs.
Okay.
So if you take that 5 and you add any of those numbers, I think the 51 will get you the closest.
Okay, you're saying, giving me some kind of an argument that we want every team to be as average as possible, and that by doing this, every guy's team's going to be as average as possible. Maybe that's an argument, but I don't know if I believe that. I think I like the idea of a contradiction proof, but I want a full contradiction argument, okay? So what is the contradiction argument that I want to try? I want to say, okay, this algorithm, how am I going to assume this algorithm is correct? I'm going to prove by a contradiction. Suppose it wasn't correct. What would that mean? that would mean that there is a set of numbers here, okay? What are we at? 1, 2, 3, 4, 5, 6, 7, 8. There is a set of numbers where the, what you call it? The, let's try it like this. There's a set of numbers where the, what you call it? Where you're telling me that this has a smaller maximum sum than this. Okay? And I'm going to say, oh yeah? Well, tell me which one is the biggest pair. Okay? And if you tell me that the biggest pair in yours is, let's say, this one. Actually, I would like, and now suddenly wanting colors. Suppose this is the biggest pair. What do we know? We know that this sum from here to here is bigger than would have been the sum in this one. Does everybody kind of see it? If you're showing me one that is not made up by this algorithm, I'm going to say, show me the biggest pair. If the biggest pair happens to be one that was produced with, what you call it, if the biggest one involved using the third smallest against the fifth biggest, note that this pair is going to be bigger than what we have over here. Because the same corresponding thing, this one is in the old set, this one is in the old set. Okay? This one over here is going to involve a big value being assigned, this is going to be a small value, assigned a bigger pair than this one did. Okay? And this sum has to be bigger than the sum in the corresponding one. Okay? And actually, I'm fumfering on this a little bit. Okay? But this is kind of the idea here, is you want to take a look at it, and the key point is that you're going to say, where is the biggest pair? If the biggest pair is, what you call it, involves this one being tied up with this one, well, what do we know? Okay, this pair, I'm going to argue, is going to be bigger than every corresponding pair in this one. Okay, because you can make the one that's paired with the bigger one is going to be smaller. Okay, any questions about that? Okay. It should be clear, again, I'm feeling a little fumford in what I'm doing. You have to sit down and be a little careful with that. But it should be clear this requires a proof of correctness. This is one of an example of something that isn't obvious. It should be clear that the idea of a contradiction proof should be, you construct an example where there is you're going to tell me that there has to be an example where this one is worse than this one. And then you got to show that this one can't be worse than this one. And that I have to probably work out a little more carefully than I have done so far standing up here. Any questions about that? Any questions about the general thing? Okay? Okay, fair enough. Let's move on. What I'd like to talk about, this was an example of an algorithm for something that was, what you call it, done by sorting. And sorting ends up having lots and lots of, appearing in lots and lots of algorithms. Sorry if I can't get this quite right. Okay? You've probably taken a zillion programming courses so far where you have talked about sorting. I know you have talked about sorting in 1.14. You have probably talked about sorting in 2.14. You may have talked about it in 110 or something like that. Okay? Why is it that I like talking about sorting and anyone with algorithms talking? Well, historically, sorting involved anything that involving data processing was basically sorting. So sorting was an important thing to get right. Another thing about sorting is that it's probably the algorithm problem that has been most heavily studied. There's a wonderful book by a fellow named Donald Knuth on searching and sorting, and it's incredible how deep and intricate the analysis is of so many different sorting algorithms. This is something computer scientists know how to do. But probably the best reason why we're going to talk about sorting in here is that there's lots of different algorithms based on different kind of algorithmic ideas. And they are good examples of how these algorithm ideas are used. So the reason we're going to talk about quicksort and the reason we'll talk about Heapsort is that there are lessons in there, okay, related to algorithm design. Any questions about that? Again, I'm going to trust that you've seen many of these algorithms before, but I'm probably going to concentrate more heavily on the analysis at this point. Okay? Any question? Okay, so what am I dealing with? So, okay, I'm sorry I'm having some trouble here with this new thingamabob. Let's try it. Okay, so why is sorting, a fast sorting algorithm is important? Remember, the dumb sorting algorithm you learned first was something like bubble sort or insertion sort. Those were n-squared algorithms. We saw in a problem, the previous problem of the day, I think we saw 3 or 4 different n log n algorithms that would sort if you just so long as you have balanced binary search trees. In fact, when you look at for large n, the difference between an n-squared algorithm, even something n squared over 4 or something like that, compared to an n log n algorithm, simply becomes enormous. Civilization could not have existed. Modern civilization could not have existed if we did not have n log n sorting algorithms. Because if you wanted to do any kind of data processing on big data, it would have been impossible if we had to use a quadratic algorithm. Even for 1 million or 10 million items, you can sort in a modest amount of time. If you have an n log n algorithm, with an n squared algorithm, hopeless. Okay? Any questions? So really, the difference here is actually an important difference. How do you use sorting algorithms? Okay, I'm having trouble here, officially having trouble here today. How do you use sorting? Sometimes people ask me with sorting, are we sorting in ascending order or descending order? This is not interesting in an algorithmic sense. Why not? Because the details of what exact order we want from our sorting is usually can be deferred to a comparison function. Quicksort to get things in an ascending order is the same as quicksort to get them in a descending order. The only thing that differs is what is the key, what is for any 2 keys, which is the one you want first in sorted order. In ascending order, you want the small one first. In descending order, you want the big one first. In general, when you're trying to build a real fancy sort for names and things like that, you have to keep in mind that there are more complicated decisions about what should be first or not. Okay? When you're sorting things, should capital Skeena appear before or after or in the same place as little Skeena? Okay? That depends upon whether capitals are treated differently than letters. Are hyphenated names, is the hyphen before or after a blank? If you don't care about it, you use the default collating sequence of the character set. If you do care about it, you have to write a function that explicitly given 2 names decides which one goes before the other okay, given a comparison function, okay, that given a pair of arguments tells you which one is first, you can then use sorting to put things in whatever order you want. Any questions? That should be clear. Should also be clear that sorting, in general, you have to worry about equal elements as well. There can be duplicates in a data set. And sometimes, in principle, when you sort things, what you probably want are all the equal keys to bunch together. Okay? One thing that I'm going to mention, which is, something to keep in mind, when you say something like quicksort is n log n, actually, if you have a quicksort that is not implemented extremely carefully, quicksort on n keys, all of which are the same, could very well be n squared, okay? Because exactly what you do with duplicates, if the duplicates kind of run together, you want to treat them as a block. If you don't do something explicit for that, sometimes, you get into certain problems, okay? Often, though, even if keys are the same, the elements are not the same. There's often secondary keys, okay? So if, let's say, if I sort this class by last name, there's probably going to be some duplicates. The way that's resolved, of course, is then by using the first name, which is an extra key, okay? Bottom line, we're going to assume a comparison function that you implement that will tell us for any two records which one would go first or second, okay? And when you use any kind of a library function for sorting, again, I happen to like the qsort function in C, just because of the way I do it. It will take arguments that will tell us sort the array started with base, where the array has elements of size this many bytes, okay? No, it has n elements, so it's an array of n elements. That's the second argument. The third argument tells me how many bytes is each element. If I'm sorting characters, each byte is one element. If I sort an integer, each byte is probably 4 elements. Each integer is 4 bytes. And the final argument is a comparison function that takes as input 2 arguments and returns either 1, okay, if I is greater than j, okay, minus 1 if j is greater than I, and 0 if it is the same. Any questions? Okay. So if you are in practice going to be doing sorting, you should use the library function. I'm going to spend the rest of class, and in fact the rest of the next several classes, telling you about lots of different sorting algorithms. But in practice, usually you can get away with a library function. Any questions? Okay. Now, what makes sorting algorithmically interesting is that one of the things that's important is that there are many, many problems that basically get solved by sort something, okay, and then do something. That sorting runs in n log n compared to n squared is a minor miracle, okay? I mean, we're used to it, okay? Often, a lot of n squared algorithms can be reduced to n log n by realizing that if we take the data and sort it in an interesting way, okay, something interesting is going to happen. Okay, so what can we do with sorting? The first one, you probably know, is for speeding up searching. If I have a sorted array and I want to look something up, it should be clear that by binary search you can find it in log n time. That's one reason why we like to sort. Any questions? Okay, good. But there's other more clever problems. Suppose I have a bunch of numbers here, and I want to find which pair of numbers differ by the least amount. Okay, what's the closest pair of numbers there? Okay, if I wanted to figure out which are the 2 students in this class whose GPAs are most similar. How would I do that efficiently? Okay, there's n students in this class. If I wanted to find out which two of you have the most similar GPAs, what would be the way I should do that? Yeah? Sort the students, and then what is the important point?
You can do compare the difference.
What's clear is after sorting, the two most similar GPAs are going to be next to each other. Does everybody kind of agree with that? If they're next to each other, we can now walk through the array and compare each of the n pairs of neighboring points and say, what's the size of that difference? A linear scan through that, okay, will enable us to find the closest pair. Any questions? How many people see that? I don't feel I'm communicating well today. How many people see why you can find the closest pair among n numbers in n log n time? Okay, anybody who doesn't see it has any questions? Okay, so that's good. Okay. What about knowing whether or not the n items in this thing are all distinct? Let's say you have names that are on a mailing list you accumulated somehow. Suppose you want to make sure you're not going to send mail to somebody twice. How do you identify test that whether all the elements in your array are distinct? Yeah? Okay, so one thing you're saying is, oh, use a hash map. And on some level, that might very well work. If you what could do if you used a hash table? Okay, that's what you're really saying, right? Well, what would happen if we built a hash table? Okay, if we did a hash table where we were resolving it with buckets, the same name, even if it occurred twice, will go into the same bucket. Does everybody kind of agree? Generally speaking, what should happen, every name is going to get hashed to a bucket, okay? If we have a very good hash table, hash function, and everything works out right, it should be the case that if the values differ, each list is going to be small, of constant size, and then walking through the list and sorting each individual list, which is probably going to be constant size, you can distinguish the case between two names that are the same versus two names that happen to get hashed to the same bucket. Does everybody kind of see that? Any questions? I'd like some feedback now. I'm getting no looks from people today. Okay, do people see how using a hash map should, in principle, be good at this? Because you're going to get them into hash things to buckets. Each bucket is going to have a constant number of items unless there are duplicates. Okay, you could imagine a world where everything in your array was the key schema, in which case you've got one long list with a lot of things on it. Okay? But generally speaking, things will you're going to end up with short lists. You can sort them and check them. A hash table is in practice a perfectly good way to solve this problem. Now, what happens if you get unlucky with your hash function, though? If you got unlucky with your hash function, all the keys would get hashed to the same bucket. And after you spent a linear time building this thing, you wouldn't necessarily get there. Okay? So the worst case for building a hash table is still going to be something like n squared. I mean, if you're going to take or all the elements ended up in one bucket and then you had to sort this list, we agree that by hashing you didn't accomplish any good in the worst case. Usually you're going to do just fine. Yeah?
That's like a chain hash map, right? What if you did like the quadratic version?
Okay, so what if there was a different way of building a hash table? There are other methods for collision avoidance, which I didn't really talk about last class. class, like using quadratic probing or something like this. The same problem happens. It all depends upon how good the hash function works with your keys. If all the keys are going to be hashed to the same bucket or hashed to the same value, then on the secondary thing, they're also going to be hashed to the same value. Okay? Depends upon the details. Take it back. Let me take that back a little bit, depending upon how you implement the hash table. But in general, with the problem of collisions, in the worst case, you have no guarantee there won't be collisions. And that in the worst case, you won't do any good. This is generally much too pessimistic. So in practice, for an expected time thing, the hashing is a good idea. How long would this take? What is the expected time for finding out whether all the elements are unique if we use hashing? O of n. Does everybody see that's linear? Okay? Because we could build a hash table in linear time. Assuming all the lists are short, okay, we're going to find if there's a duplicate or not in one linear sweep. So hashing is a good way to do this in practice, but it's an expected bound, not a worst case bound. What if I want to be good in the worst case? How would I tell? Yeah?
Maybe creating a set and then adding to the set, like walking through the set of n items and then checking, like create a new set and then add to it and then check if that value exists.
Okay. So you're saying using sets. Sets seems to be some kind of a complicated thing built into your programming language. Okay? I want us to talk about the lower level ways of implementing it. So the way I would be doing this is I would take the elements and I would sort them. If I sort them, how will I now know whether or not the elements are unique? What would I have to do? Yeah? Check whether neighbors are equal. This is actually a special case of the minimum gap, right? Before we wanted to find out what were the two students with the closest GPA. Here we're asking, are there two students with exactly the same GPA? By comparing the neighboring elements, we would be able to find that. So it should be clear that we can solve element uniqueness by sorting and walking. And that's going to be n log n in the worst case. And you're right, in practice, hashing is a good thing to do with this. Okay? We're going to wear two different ways of thinking about the world. One, what is practical because it's going to get me a job, and hashing is the right answer here. The other is, what's going to get me a good grade on the midterm when he asks for a worst case bound. And that's where you want the sorting algorithm. Any questions? Okay, good. What if you want to find the mode of a set of numbers? What's the mode of a set of numbers? Okay? It's the value that occurred most frequently. Does everybody kind of agree with that? So if I take a look at this class, if I wanted to know, if let's say we take a look at, I'm trying to come up with a cutesy number thing, but let's say, you guys have we have your GPAs, okay? The mode of the GPA would be the GPA that occurred the most frequently. What do we think the mode GPA is in this class? Okay, the most frequent GPA of any that's had in this class. My guess is GPAs are kind of floating point numbers, so there's probably not that many collisions. Maybe it's actually 4.0, because it might very well be that two people have perfect GPAs, okay? Any questions about that? Okay? The mode is the most frequent number. So again, 3, 5, 3, 2, 1, 3, 3. The mode is 3 because it occurred 4 times. How would we find the mode of a set of n numbers? Okay? Does anyone have a proposed algorithm? If you want to find what value occurs most frequently, which one is it? Any ideas? If you want a good worst case algorithm, what should be the first step? Yeah? Sort it. Now what happens when you sort it? Yeah, now that it's sorted, what's good? So we agree sorting is a good first step. Why is it a good first step? So we know that once they are sorted, all the blocks of three, the block of threes will all be next to each other. Does everybody kind of see that? And once we see that, then how can we go and count how many times this occurred? Well, we can kind of walk through our array again, but with two fingers. We start with the first element. How long is it? Are you the same as the first element? Are you the same as the first element? Are you the same, not the same? Well, we have a finger here and a finger here. The difference between them is 2 plus 1, that's 3. Now we try this game again. Start both fingers here, okay? The distance there is going to be 1. Does everybody kind of have this idea that we're going to look? When we start a run of elements, we're going to walk down the other side, okay? And count there how many times it occurs. Then we're going to avoid going backwards by starting on the next position. We're going to spend a total of order n time to figure that out. Any questions? Okay? So in n log n time, in the worst case, you can compute the mode. Now, how would you compute the mode in using hashing? You want to do hashing a lot. What would be the way that you would do hashing? Use it for hashing.
You have the keys represented as the value of the array, like for example, 1 is key maybe 1, and then you just increment the value that it points to, and then you see the value.
Okay, I'm not sure I heard that completely, but I do think the idea that you start by building a hash table. Wherever the mode is, there's going to be a list with all the elements on it. Your job is to sort that list, okay? In general, because once they're sorted, you can do the block kind of analysis here. Yeah?
It would be more like the number in the array would just point to a counter inside the function. Then you just increment the counter each time you see it.
Okay, another way that he's doing it now, which sounds even better to me, is what if we have an array of records that we're building our hash map to, which consists of, we're not putting the numbers in the hash table. We're putting records of the form key with a counter on it. Okay? And now when we do this, okay, whenever we look for, whenever we want to increment, whenever we insert another element, we're going to first start by looking, is it in this list? If we had a good hash function, there should only be a constant number of distinct elements in this list. If we find it, we increment the counter. If we didn't find it, we insert a record with a count of 1 on that list. Okay? This should also be linear time. Okay? Does everybody kind of see that? So expected mode time would be linear. Okay? In the worst case, it takes n log n because you need to do the sorting. Any questions? Okay, so hashing is a good thing in practice. That's one thing that should be clear. Any questions? What if you want to find the median element? What is the median element? Okay? The median element is the one that has the same number of elements greater than it as less than it, right? How do you find the median?
Actually, I have a question about the last line.
Yes.
How do you find it mentioned log n time using binary search to find the range of this? How does that work?
Okay, so there's another extension to this idea that how would you go, let's say that I gave you a sorted array. Okay, this is a separate question that I'm asking now. What if I gave you a sorted array and I wanted you to ask how many times I wanted you to find out how many times did 3 occur in this sorted array? Okay? We agree that by doing binary search, you should be able to find an element that one of the threes in logarithmic time. Do you agree? If we wanted to count now, how many times does this occur? How would we do it? One way to do it might be keep walking up from here until you see a transition, and keep walking down from here till you see a transition. That would take as many steps as there are individual elements. Does everybody agree with that? If the whole array was threes, this would take order n time. Okay? Now, what would be another way I could find out how many threes there are? What if I look for the number 3 minus 0.0000000001? Where is that going? Especially if these are integers. Where is 3 minus 0.001 going to be? Well, if it's not in the array, okay, we're not going to find it, right? But we're going to be able to, in the course of a binary search, know that if it was going to be, it was going to be located here, right? And now if we look for 3 plus 0.000001, we would learn that it would have been here. Does everybody agree that subtracting this index from that index will tell me how many elements there are, right? So I don't actually, if I could get away finding the exact number of elements in order log n time instead of order log n plus k, where k is the number of times it occurred. Okay? Any questions? Okay? Again, there are a lot of interesting tricks you can do with searching and sorting, and that's good. How do we find the median? What's the most effective way to find the median? So the median is the element that has the same number of elements above it or below it. Does anyone want to propose an algorithm to find the median? Okay, how do you find the median? Yes? Sort it, and then when it's sorted, look at the n over second position. That's got to be the median. Does everybody agree? These many elements are less than it, this elements are greater than that. That's going to be order n log n to sort it, and constant time to then look it up the right answer, because it's in an array, right? Yeah? Then there's a question of how do you define the median, if it's even, if there's even or odd. Well, again, you can look at a constant number of things here and either average them or do whatever you want, okay? So it should be clear that by sorting you can find the median, right, in n log n time. How do you use a hash table to find the median? We've seen hash tables seem all powerful. How do you use a hash table to find the median? You can't, because there's no, it's not, a hash table would not do you any good to find the median. Okay, this is an example of something you couldn't really do with hashing. Okay, again, there's some very, very powerful hashing ideas, so I don't want to really commit to that. But certainly based on what you guys know, I would say you can't use hashing to find the median. Any questions? It turns out there is an order n time algorithm to find the median, okay? But it turns out to depend upon ideas from sorting. You're not going to completely sort it. You're only going to sort it on the right part of the array that matters, okay? But we'll file that away for later. Any questions? Again, there are lots of other things you can do with sorting as a building block of algorithms. Let me spend 1 minute talking about this idea. Some of you are destined to take Professor Mitchell's computational geometry course. Has anybody taken it or done that? Okay. You probably learned about Convex Hull. What is Convex Hull? It's kind of the simplest thing to do it with points in 2 dimensions to some extent. What is it? It's to connect them into the smallest convex polygon that contains them. Okay? How do you compute convex hull? There are a bunch of different algorithms, okay? But all of them generally reduce to basically an idea like sorting. Let me try to convince you. One observation is if you take the points and you sort them according to the x-axis, you can insert each point knowing that it's going to be on the convex hull of all the points before it. Okay? The convex hull is the outside boundary. If we take the first 3 points, does everybody agree they form a triangle and that's convex? If we take the point with the next highest x, it's got to also be on the boundary because it's got a higher x. It's not inside the region so far. So we know it's got to be on the hull, and we can insert it, if we're clever enough, in a way that's pretty quick to do the insertion. The next point in sorted order has to be on the outside. Has to be on the outside. Has to be on the outside. Okay? And so basically what convex hull algorithm, or at least some of them do, is sort the points, knowing the next point is going to be on the outside, now fix the hull to remove the stuff that's now inside. Okay? And all of that turns out to take linear time once you've done the sorting. Any questions? Okay? So sorting is an important thing to be doing here. Any questions? Okay, let me try to erase that. Okay. Erase. What do I got to do here? Boom. Oh, wait, hold on. Okay. So now, any questions about applications of sorting? A lot of the homework problems and algorithm design problems reduce to calling sorting in the right way. Okay? What I'd like to now talk about, though, are algorithms for sorting efficiently. And, you know, there are a few ideas that come up in these algorithms that are worth noting about. One of the ideas is that by using a better data structure, you can improve the right data structure, you can improve certain kind of algorithm ideas. And the case in point I'd like to start off with is selection sort. Does everybody remember selection sort? Selection sort was one that went through all the elements, found the smallest element in the array, put that one first, and then went through all the rest of the elements and sorted and found the smallest and kept doing this. Okay? It found the smallest remaining, smallest remaining, smallest remaining. Selection sort looked like this, if I am correct. Okay? You have a loop that goes around n times. Find the smallest element of the remaining n minus I plus 1 elements of the array. Pull that out of the array and make it first. Okay? Does everybody agree that this is selection sort? Any questions about that? Question like, I don't know what selection sort is a good question. Do I need to do an example or not? Okay? What is the running time of selection sort? Okay? Does anyone remember what the running time of selection sort is? Yeah? N squared. Now, why is it n squared? How much time does it take to find the smallest of the first n minus 1 n elements in the array? How much time did that take? N. And how much time did it take to pull that element out of the array and make it first? Oh, of 1. That was just a swap, right? And this was going around n times. That's because the reason it was n squared was it was n times n plus 1, right? Now, my question is, if we look at these two operations, selection sort does take n times the time it takes to find the min and to do the swap. Is there another data structure that we could use other than an array that might realize different time bounds on these two operations? Okay? If you look at this, one of these operations takes order n time. One of these operations takes order 1 time. If we could find a way where we could both find a data structure where we could both find the minimum of the elements and pull out the minimum of the elements, if both of those operations took log n time, does everybody see that that would yield us an n log n algorithm instead of an n squared algorithm? Okay? So is there a data structure where we can find the minimum element in the tree, in the data structure quickly? Have we talked about such things? Yeah? If we had a binary search tree, does everybody see that a binary search tree, a balanced binary search tree data structure, would let us do selection sort, okay, in n log n time? Because it has the min operation, bop down the left pointers. It has the delete operation, okay, so we could take this element out of the tree, okay? It should be clear, the lesson somehow of selection sort should be that if we have the right data structures, we can do it faster. Okay, I'm sorry, I want to make that clear. Sorry about this. Let me erase it here. Okay, if we use, if we used a balanced binary search tree, we would achieve a better balance of those operations, and it would take n log n time to do selection sort. Now the trouble is, balanced binary search trees are complicated things. We didn't do balanced binary search trees in detail in this class, because maintaining the balance is complicated. What I'd like to say is, in general, you should always be thinking, is there a better data structure that realizes the operations that we want? Okay? And if we have it, again, balanced binary search trees will do it. But there is another data structure, or a simpler data structure, that will do it. Okay? And I'd like to spend the rest of the class talking about heaps and priority queues, because those are simpler data structures that will enable us to find the minimum of all the items that are there, find the minimum item, and to delete the minimum item, and to allow us to insert new items into it. Okay? That's what priority queues are. They're data structures that do the operations. Insert, given a key, insert it in the priority queue. You either have a minimum priority queue or a maximum priority queue. One way, again, it's just like negating all the values. Okay? Typically, find min. Find min is an operation that, given a queue, finds the smallest of the two items. Okay? Delete min is an operation that, given a pointer to given the priority queue, finds the minimum element and deletes it. Okay? Any questions? For priority queues, okay, we could use balanced binary search trees and do all three of these operations in log n time. Heaps are going to be a simpler data structure that does all three of those operations in log n time. Any questions about it? Okay. Just like with sorting, one of the reasons to know about sorting is that there's lots of applications of it, like finding mins and medians and stuff like that. The thing that's interesting, it's important to learn how to think in terms of priority queues, because they are data structures that have come up in lots and lots of problems in in algorithms, and also in life, okay? How should you organize your dating life? Okay, I shouldn't make you too many suggestions, but I am going to guess that you organize your dating life in a way that is actually modeled by a priority queue. What is it? There are a set of candidates you may want to date. Every one of these people has a priority, a value. Okay? Typically you want the one that's the best. Let's say value increases. You would like to be able to date the person that has the maximum value. Okay? What is the dating process? You say, find me who's the best person that I would like most to date. Retrieve them by value. That's what it means. You then call them up, they turn you down. Okay? Now that person you're going to either take out of the priority queue or insert them in the priority queue with a lower value. I'm not going to call them again. What is the point? Does everybody kind of see that desirability is the thing that you want to organize the data structure by? And that's what priority queues do. They organize, you don't retrieve keys by name, you retrieve keys by value. Any questions? Okay. When you're doing simulations of things, often you want to have events simulated, and you may be building a simulation where things happen at particular times. You could imagine that at a certain time in an airport, a plane's going to arrive. You know when planes are going to arrive because that's what's scheduled, right? But if you want to now do operations and simulate the airport through time, you always want to know what is the next event that's going to happen. In many kinds of simulations, okay, you're going to want to use a priority queue to, to maintain what is the next thing that's going to happen or the next job I should work on in a world where there are jobs coming in, there are jobs going out. Okay? Any questions about that? So priority queues are very useful things. Okay? And the heap is kind of the simplest good priority queue. And I'd like to spend the rest of the class talking about heaps. Any questions? So what is a heap? A binary heap is a binary tree, not a binary search tree, but a binary tree with a key in every node, which has a very, very, very balanced shape, the most balanced possible shape you could have. All the leaves are going to be on at most 2 adjacent levels. Okay? All the leaves on the lowest level occur to the left as much as possible. And only the lowest level is the one that is not completely filled. Okay? Any question? That's the shape of the heap. The other question is, what is the labeling of the heap? The property that we want in a heap is that for every node, okay, the root node is less than all of its children. And this is true for every single node in the tree. Okay? The minimum value is the root. Okay? Every node is smaller than its children. Okay? This is the labeling property that's going to make it very, very easy to find the min, because the min is always going to be at the root. Any questions? So here is an example of a binary heap, and I want to make sure people kind of get it. These are years that are in history. What do we know? We have the shape of the heap is as specified. The leaf nodes are all on the lower 2 levels. Does everybody kind of see that? And that the only level that is not filled is the very, very lowest level. Okay? Correct? Does everybody see that in a binary tree, obviously everybody has two children? Okay? In our heap, the shape of the heap is what we want here. Okay? And the heap order property is what we want. For every value in the heap, the root is smaller than its children. 1492 is smaller than 1783 and 1776. 1804 is less than its children. 1783 is less than its children. Does everybody kind of have that property? Every node is smaller than its two children. Okay? Where is the smallest element in a binary heap? Okay? Where is the smallest element? Yeah? The root. This has to be the smallest element. Where is the second smallest element in a binary heap? Yeah? It's got to be one of the two children. In this case, the second smallest happens to be here. Does everybody see that? Where is the third smallest element in a binary heap? Okay? Where can it be? Yeah? It could either be here, or here, or here. Right? Does everybody kind of see that? We know it's got to be less than the nodes that are there. It's got to be the biggest. Uh-oh, that's going to be a challenge. Shoot. How do you like that? There. Okay? Does everybody kind of see that? Where was it? It turned out that the third smallest one was here. The fourth smallest could be any one of these other ones. 1, 2, 3. Right? Now, if they were sorted, the elements would be sitting in an array, and it's easy to find the third smallest. The third smallest would be sitting in third position. Does everybody see that the heap provides less structure than a totally sorted array? Okay? But because of that, it might be easier to construct. Okay? Any questions? What's a great property of the heap? Because it has this thing that it stuffed the array as much as possible. Notice that we can represent the values in a heap by elements in an array without pointers because we know the structure of this thing. What if I put the first element in the first spot? If I read the elements going along, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, does everybody see that if I read the elements off layer by layer, I can put them in an array? Okay? The interesting thing is that for every node, the element I, its children are going to be in positions 2i and 2i plus 1. What is the children of node 3? According to this, its children should be in positions, let me just make sure, okay, the 1, okay, wait, oh no, this is not node 3, excuse me. This was node 3. Does everybody see that the third element in my heap is this one? Its children should be in positions 2 times 3, or 6, and 7. Does everybody kind of see this property? Okay. If we stick the elements in the heap, okay, in an array, okay, by walking along each layer, okay, then we have the property that we can look up the children of any node in constant time, okay, without accessing without needing pointers. Any questions about this heap order property? Okay? So I'm going to assume everyone now understands what the heap is as a tree, and because of how it was built, we can actually store that tree in an array without needing pointers, which is very nice. Any questions about that? Okay, good. That's basically what I'm saying here, okay? That we can implicitly store, okay, heaps, okay, in arrays, okay, because if we encode them with the property that node i's children lie in positions 2i and 2i plus 1. Any questions? Okay. How can we build a heap? Okay. I want to say we could build one incrementally. Suppose I've got a, and again, I like to think of it in terms of as a tree, although I know I can store it as a, I know I can store this as a array. What if I want to insert another element into a heap? How could I do that? Let's say my heap was, let's make it 38, 16, 25, let's say 4, 7, 10, 8, 1, 3, and 6. Suppose I want to put a number, insert something in the heap. How do I do it? I am going to put it into the next slot in my array, meaning the next element on the lowest level. Okay? Suppose I put a number here that is greater than 8. Is it going to be a heap if I put a number here? Let's say I put a number here that's less than 8. Is this going to be a heap if I put a number here that's less than 8? The answer is every element has to be less than its parent. So yes, if I put in a 5, everything is good. Does everybody see that? What happens if I put in an element that's bigger than an 8? Okay, let's say a 9. Is this a heap now? Or does it not have the heap property? It doesn't have it because this element is bigger than the parent. What can I do to restore this as a heap? Does everybody believe, let's say I put a number like 19. Let's make it a big number. What I could do is if this element is bigger than its parent, I could swap it. Okay? Now what has happened? This node is now bigger than what it was. Does everybody see this? It used to be an 8. It has gotten bigger than an 8. Is this node going to be happy with that swap? It has to be less than its parent, but its parent got bigger. Does everybody see that? Okay. Is this now a heap, or do we have a problem still? Is this a heap, or is there a problem? Problem. What's the problem? This element is bigger than its parent, right? So again, at this point, we could do another swap. This node is going to be perfectly happy because its parent just got bigger. This node might be unhappy because its child just got bigger. But in fact, it is less than its parent. This is now happy. Does everybody kind of see that? If we have n elements in the heap, what is the height of the heap? Okay, this is an important thing to see here. If we have an n elements in our array, what is the height of this heap going to be? Log n. Why is it log n? Now we're talking. Now you say it's been doubling, right? We started with 1. We could fit 1 element in a heap on one level. We double it. Now the number of leaves is 2, 4, and in a balanced tree, the number of leaves is going to be n over 2. Does everybody see that? How many doublings do we need till we get n over 2 leaves? Well, it's going to be log n, right? So what does this mean? A heap is going to be of height log n. We can do insertion by adding each element in until it, by propagating it upward, filling it in the next slot, propagating it upward, and keep doing this until it runs out of room. Any questions about that? Does everybody see why insertion takes log n time? Okay, fair enough. And this is the algorithm that basically does that, okay? Any question? I'm not going to look at the code now, but you should understand it. Now that we've got a heap, the other operation we need to support, finding the maximum in this case is easy. The maximum has to be at the root. How do we delete the maximum? Suppose we delete the maximum. We want this value to get out of the heap. Okay? How do we restore it to being a heap after we delete the maximum? Okay? Yeah? Swap it with a leaf node. Not only a leaf node, but there's only one leaf node we're interested in if we want to maintain the shape of the heap. What is the leaf node that we're interested in, yeah? The rightmost one. We put this guy in there, right? And now, is this a heap? Well, it would be a heap if this guy was the biggest value of all, right? Given that he previously lived in the lower part of the tree, he probably isn't, right? How can we restore this to being a heap? What operation do we have to do? Where is the maximum element remaining in the heap? It's got to be either this one or this one. Does everybody agree? Why don't I now find the bigger of them and swap them? Does everybody see that? Is the other one, the one that was second biggest, is he happy? He's happy because someone bigger than him is his parent, right? Is the root node happy? Well, he's now on top, and he's bigger than both of his children, so he's happy. Who is unhappy? Okay. Well, actually, in this case, nobody is unhappy, right? Because this element is bigger than both of its children. But suppose that this was, in fact, a value 17. Now, is this guy happy? No. Does everybody agree that he can be swapped and he will slither down to the right place where it's going to be? So what is the operation now about fixing the heap? It should be clear that we're doing a constant amount of work. Compare the node value against its two children to decide which of the three is biggest, do a swap, and then push the problem down one level. In constant time, we have moved the node down one level. By comparing its two children to that new node, we will decide whether we still have a problem or not. We can have at most log n problems, okay? Because each time we do it, we push the problem down one level, okay? And we can do it in constant time because we're only comparing each one of these things. I claim that extracting the minimum element also takes logarithmic time. Any questions about that? Okay. Do people see where the log comes from? This is the biggest thing to see here. We know that the height of a binary heap has to be logarithmic in height. Why? Because how many nodes are there? There's 1, 3, 7, 15. There are 2n minus 1 nodes in it on a tree of n levels, right? The number of nodes grows exponentially with the level, meaning the level grows logarithmically in the number of nodes. A heap is a tree of height log n, okay? Fixing these things, we're doing a constant amount of work and moving it down. Any questions about that? Okay, do people see why we can implement all these operations in heaps in, logarithmic time? Any questions about that? Okay. Maybe, given the time that I have left, what I'd like to talk about is, maybe let's just go through the code to make sure we understand this right. How did we insert the operation? Sorry. Now this is bad. Okay, hold on. What was my code for insertion? Okay, my code for insertion was, if I want to insert an item into a priority queue, assuming I haven't exceeded the bounds of my array, what am I going to do? I'm going to enlarge. I'm going to now put my new element in the n plus first position. Okay, I am going to, set that, I'm incrementing the size of my array. Now I have n plus 1 items. I'm going to put my element in the new blank, and I'm going to bubble it up. How did bubble up work? Well, if the parent of a node was not an extreme condition, okay, if the parent of a node we were saying was minus 1, then that meant that we were at the root. Okay, assuming we're not at the root, okay, what are we going to want to do? We're going to want to compare for a given pth element against its parent. If the relationship of my element to my parent is not what it should be, then I've got to move it up. I swap the two elements, and then I recur on my parent of my parent, okay? And that's what happens. Does everybody see how this does the bubble up procedure that I used with the insertion? Any questions about that? As far as the second part of the thing that I was telling you about, the deleting the maximum, what did I do? Basically, if I try to delete the maximum element and my queue is empty, I'd better complain. If not, what am I saying? The minimum element, okay, and this I'm extracting the minimum. The minimum is in the root. If so, return the value in the first position. Otherwise, replace it now with the element that is in the nth position. Okay, that leaf over there. Okay? Decrement the count of the number of elements that are in there, and now do the bubble down procedure. What was the bubble down procedure? Well, basically what I'm going to want to do, I have a loop here, but notice this loop is going between 0 and 1. It's looking at two possible values. Okay? Basically, if I am at position I, the children of position I are going to be in position 2 times I and 2 times I plus 1. Okay? I am going to, basically compare myself to each of these. Okay? And figure out what my minimum index is. Okay? Once I know which one of my children has the smaller value, if the one with the smaller value is not me, Okay?